All right, welcome to lecture 2 of Math 340. Today we'll talk about subspaces, which is section 1C in your textbook. Okay, so what's the definition? A subset U of a vector space V is called a subspace if U is also a vector space using the same addition and scalar multiplication as V. Okay, so recall that V is always a vector space over F. Okay, so this definition says, given any subset, you say that the subset is a subspace if it also is a vector space. So it also satisfies those 7 properties from last time. And again, the important thing is that since it's a subset of V, V has an addition and a scalar multiplication, right? So you know how to add 2 elements of U because they're both elements of V. But for example, that sum needs to also be inside of U. Similarly, you know how to scalar multiply because you know how to scalar multiply vectors in V and use a subset. Okay, so a subspace is just a subset that is also vector space. Now, how can you tell if something is actually a vector space, actually a subspace? So here's the proposition. A subset U of V is a subspace if and only if it satisfies the following 3 conditions. So first of all, 0, the 0 vector has to be in U. Second of all, if U and V are in U, then U plus V is in U. And third, if alpha is a scalar and U is a vector in U, then alpha U is also in U. Okay, so these 3 conditions are just that you contain the 0 vector. This is just to prevent sort of edge cases like the empty set. So the empty set is not a subspace, right? Because it doesn't contain the 0 vector. And then this condition, right? You're closed under addition. And this condition says that you're closed under scalar multiplication. Right, so if you satisfy these 3 properties, then you are a subspace. So it's if and only if. So let's prove this. Okay, so I guess we'll do this direction first. So if U is a subspace, then by definition, it's a vector space using the same addition and multiplication as V, right? So 2 and 3 are automatic by the definition of a vector space, right? If U is itself a vector space, then it needs to be closed under addition, right? Every vector space has to have some operation called addition, right? It needs to be closed under it. So here we're using the operation in V, but if U is going to be a vector space, 2 is automatic, same thing, 3 is automatic. So if U is a subspace, then it is a vector space. And a vector space is supposed to have 2 operations on it. In particular, those operations should be closed. So then 2 and 3 are automatic. Okay, so in some sense, it seems like 1 is automatic as well, right? Because a vector space needs to contain a 0 element. The thing that we should check, though, is that the 0 element of U is the same thing as the 0 element of V, right? Because this 0, this one here, refers to the 0 vector in V. We know that U has an additive identity, but we don't know that it's the 0 vector of V. Right? So we should check that the 0 vector of U is the 0 vector of V. Right? But note that say you have the 0 vector of U, whatever it is, it's also a vector in V. So if you scalar multiply by 0, the scalar 0, you get the 0 vector of V. right? This is because this is true for every vector in V. And because U is closed under scalar multiplication, this means that the zero vector of V is definitely in U, right? Because this is a vector in U, here's a scalar, so when you multiply, you need to get a vector in U. Okay, and also 0V is clearly an additive identity of U, right? The zero vector of V has a property that 0 plus V equals V for every V in V, but the ones in U are already in V. Okay, so now by uniqueness of additive identity, 0V must be 0U. There's only one additive identity, and this thing is in U. Okay, what's the converse? So let's conversely suppose that U satisfies three conditions. Suppose U satisfies 1 through 3. We need to show that it's a subspace. Sorry, right? So if U is in U, well, for one thing, -1 times U, which is the additive inverse of U by the result we proved last time, that's a vector in U because U is closed under scalar multiplication, right? This is by condition 3. So this shows that U contains additive inverses. Right, so that's one of the axioms we need for a vector space. Let's actually go back to last lecture and look at these axioms for vector spaces. Right, so we just verified 4. Okay, but the rest of these axioms, which deal with the properties of the operations, are automatic because the addition and scalar multiplication in U is inherited from V. Right, so for example, this first property says that addition has to be commutative. So we need to check that the addition in U is commutative, but the addition in U is inherited from the addition of V, which already had the commutativity property, right? So you can check for yourself that the rest of these conditions follow because the addition and scalar multiplication in U are inherited from V. So the rest of the properties follow since both the addition and scalar multiplication are inherited from V. Okay, so that's the condition that tells you when you have a subspace, you should check that contains 0, it's closed under addition, and it's closed under scalar multiplication. Okay, so just some examples of some subspaces. So if B is a scalar in F, then we can consider the following subset of F3. Okay, so the set of all vectors in F3 such that, I don't know, say x1 minus 3x2 equals B, right? So this will contain some vectors, right? So for example, e.g., if F is R here, then this contains vectors like B comma 0 comma 0, right? Because that satisfies that property. Also like B comma 0 comma 1 is in there, right? So this is some subset of vectors inside of F3. And this is a subspace. Maybe I'll just say is a subspace if and only if B equals 0. Okay, so you should actually check this for yourself. But for example, the vector 0, 0, 0 is only in this set if B is 0, right? So it's definitely a necessary condition, but it turns out that that's an if and only if. here's another example of a subspace. So if you look at this, remember that this vector space, we said this is a set of all functions from the interval 0, 1 to R. So this thing is a vector space over R. We can look at the set S of all continuous functions. F from 0, 1 to R. Right, so this is some subset of functions. Not every function is continuous, but all of these functions in S live in the big vector space, right? And in calculus, you learned things like the sum of two continuous functions is continuous. Turns out also that if you scalar multiply continuous function, you again get a continuous function. And also the zero function, the function that's identically zero, is also a continuous function. And so it satisfies the three conditions of being a subspace. Then S is a subspace of this big vector space. Okay, another example. So the set of continuous functions again from this domain to R, satisfying f of 0 equals b, right? So for some fixed b, you can say, okay, let's consider all continuous functions that take on the value b when evaluated at 0. This is a subspace of R0, 1, if and only if b equals 0. Again, this is sort of clearly a necessary condition because the 0 vector in this vector space is the function that's uniformly 0. So certainly that has a property that f of 0 equals 0. So if this is to be a subspace, it needs to satisfy, I mean, you're going to need to have b equals 0, but then you can prove that if b is 0, then it is a subspace. And if it is a subspace, then b equals 0. Therefore, it's an if and only if. Okay, so you should check that these are subspaces and the claim. Okay, so this is an exercise in your textbook, but I haven't assigned it. But you can consider it like an additional exercise that you should do. Okay. So some general facts about subspaces now. So here's a proposition. So let's let U sub lambda be some indexed family of subspaces of B. Okay, so I have some collection of subspaces, one for every lambda in this index set lambda, which could be finite or could be infinite, sorry, right? Just some collection of subspaces. Then if you look at their intersection, this is a subspace of B. Okay, and this one is a homework exercise. Okay, but again, you just use the three conditions to be a subspace. You just check that 0 is in there, it's closed under addition, closed under scalar multiplication, and you'll see where you use the intersection part of this. Okay, so that'll give you some practice on subspaces as well as the rest of the exercises. The next topic of discussion in this section is on sums of subspaces. And what's the idea here? The idea is the following. If I give you two or maybe more subspaces, let's say I have two subspaces U and W of V, or maybe more than two, what's the correct notion of combining U and W to form a bigger subspace? Right, so there's many notions of combining two sets. Like you could, for example, think about the union, right? So how to combine. So you could think about U union W, right? But let me just draw a picture in R2. In R2, you know, like, for example, the x-axis is a subspace, right? Maybe let this be U. You know that the y-axis is also a subspace. Let's let this be W. But if you look at the union, it's not a subspace because if you take, say, this vector and add to this vector, you get this vector. So the union of these two things is not a subspace. It's just some subset of R2. Okay, so this thing is, in general, not a subspace. And somehow I like a notion of combining U and W to get a new, bigger subspace, right? So union won't do it. So it turns out that the correct notion is to take the sum of subspaces, right? So let's say we won't do this. Instead, we'll define the sum of subspaces. Okay, so here's the definition. So let's let U1 through UM be subsets of V. Okay, so I'm going to make this definition not just for subspaces, but even in general for subsets. But in most cases that we're actually interested in the sum, we'll take these U1 through UM to actually be subspaces. Okay, now the sum of U1 up through UM is defined to be the following. Okay, so the notation is just you take these subsets and you put plus signs in between all of them. So this is the notation. What is this set? This set is a set of all possible sums, little u1 up through little um, where ui is in big UI for I between 1 and m. Okay, so that is the collection of all possible sums of elements of u1 up through um. Okay, so this is some set of vectors in V. It's all the vectors that you can write as something in u1 plus something in u2, dot, 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 plus something in um. Okay, so I guess I owe you an example here. So let's let V be R2, just for concreteness. Let's let U1 be the set, be the x-axis, right? Let's continue the example from before. So this is all vectors of the form x0 for x a real number, and let U2 be the y-axis. Okay, as we said before, the union is not a subspace. What is the sum here? Well, U1 plus U2, what is that? That's the set of all vectors in R2 that can be written as x something in U1 plus something in U2. Right? Every vector in U1 can be written as x0. Every vector in U2 can be written as 0y. So it's a set of all possible sums like this, right? But this is just the set of all x comma y, such that x and y are real numbers. And this thing actually is all of R2. Right, so this is a subspace. And all right, let's go back to this picture. Again, okay, right, so what I called U before is like U1 in our new example. What I called W before is now U2 in our next example. So what I've done is I've like combined U1 and U2, but also I've thrown in more stuff, right? So in the end, the subspace that you get is all of R2. And it turns out that this sum, R2, ends up being the smallest subspace of R2 that contains U1 and U2. In fact, this fact is true in general. It's actually our next proposition. So let U1 through UM be subspaces now. Then the sum is the smallest subspace of V containing each of the subspaces U1 up through UM. Okay, so how do we prove something like this? So really there's two claims here, right? One claim is that the sum is a subspace, which we haven't seen yet, right? We just gave the definition of the sum. We don't know that it's a subspace yet. And then the second claim is that not only is the sum a subspace, but it's the smallest one containing all of the U's. Okay, so let's first prove that the sum is a subspace. So first, let's prove that U1 plus U2, the sum up to UM, is a subspace. Okay, so the first thing that you need to show is that the zero vector is in this subset. Okay, so I need to write, so we need to show that the zero vector, so just for ease, let's call this set S for sum. So first we need to show that 0 is in the sum. Well, how do you show that 0 is in the sum? You need to show that you can write 0 as the sum of some vector from U1 plus some vector from U2 up through some vector from UM. Well, how do I do that? Well, if I add 0 together a bunch of times, I'll get 0. And 0 has to live inside of each of these sets because they're all subspaces. Okay, so since each UI is a subspace, 0 is contained in each of them. So the 0 vector, which is 0 plus 0 plus 0 m times, is in the sum S, right? Because this one is from U1, this one is from U2, this one is from UM. So I've successfully written 0 as a sum of elements, one each from each of the UIs. Okay, so that shows that 0 is an S. So now we need to show that, now need to show that S is closed under addition. Okay, so you need to take two vectors from S and show that their sum is an S, right? So let's suppose that U and V are both vectors in S. Okay, well, what does that mean? That means that you can write U as a sum of M things, each of them from each of the UIs, and you can write V as a sum of M things, one from each of the UIs, right? So then by definition of S, you can write U as, say, U1 plus U2 up through UM, and V as V1 plus V2 up through VM, where each UI and VI is in the subspace capital UI. Okay, but then U plus V is U1 plus V1 plus U2 plus V2 plus UM plus VM. And since U1 is a subspace, this element here is in U1 because U1 is closed under addition and U1 and V1 are both in U1, right? Similarly, this element is in U2, this element is in UM. So I've taken the sum and I've written as the sum of M things, one from each U. So this thing is in S. Therefore, S is closed under addition. Okay, and then a similar, but actually easier proof. So similarly, you can show that S is closed under scalar multiplication. And you actually should do this. Okay, it's basically the same proof. You take some vector, you write it as the sum of M things. When you scalar multiply, it's like scalar multiplying each thing. But since each UI is a subspace, you'll again be able to write the scalar multiply vector as a sum of M things. Therefore, it's in the sum. Okay, but we're not done yet. So now we know that S is a subspace. But how do you show that S is the smallest subspace containing each of the UIs? Okay, well, first of all, if you have a vector from one of the UIs, well then UI is 0 plus 0 plus UI, this is in the ith spot, plus 0 plus 0, right? So you can write every vector in big UI as a bunch of zeros plus UI, right? But this shows that each of these vectors is actually in this sum, because you've written, right here, this whole thing has m terms, and in the ith slot, I've just slotted in UI. Each of the big U's is a subspace, so 0 is contained in them. Therefore, this shows that little UI is an S. So each of these big subspaces, UI is contained in S, right? Every vector in little UI is contained in S. So certainly S contains all of the UIs. Now, how can I show that it's the smallest subspace with this property? Okay, so this is one of these just general mathematical techniques. What I'll do is I'll show that if T is a subspace containing the UIs, then actually T already contains S, right? Which means that the very smallest thing that you can have that contains all the UIs is S itself. Anything else would be bigger in that it would contain S already. Okay, so to this end, let's suppose that T is a subspace containing all of the UIs. Okay, but since T is a subspace, it's closed under addition. And if it contains all of the UIs and it's closed under addition, it means that it contains every possible sum of elements from each of the UIs, which means that it contains S, right? T is closed under addition, so it contains all sums of elements from each of these subspaces. So T contains U. Sorry, T contains S. Because S is just sums of elements from the U's, T must already contain all of those. This shows that S is the smallest subspace which contains all of the U's. Okay. So sometimes we're actually interested in even something a bit more specific than a sum, something called a direct sum. So let me give the definition and then I'll give some examples. So suppose that U1 through UM are subspaces of V. Okay, then the sum U1 plus up through UM is called a direct sum if each V in the sum can be written in a unique way as V equals U1 plus U2 plus UM, where each of the UIs is in big UI. Okay, in this case, if this is true for the sum, we use the notation instead of just the plus sign, we put a circle around the plus sign for the direct sum. Okay, so a direct sum is a sum that satisfies a special extra property, some sort of uniqueness of writing the elements as a sum. Okay, so again, I owe you an example. So let's consider the following subspaces of R3. So let's work inside of R3. Let's let U be the set of elements that looks like x0, 0. Let's let V be this set of elements that look like 0, y, 0. And let's let W be the set of elements that look like x, x, 0. Okay. So each of these is a line in R3. Okay, so U plus V plus W is a subspace. Okay, and it ends up being the xy plane in R3. Okay, however, right, so again, you just take all possible sums of elements from U, V, and W, and you'll see that what you get is basically every x, y, 0. However, this is not a direct sum. Since, for example, the element 1, 1, 0, you can either write it as 1, 0, 0 plus 0, 1, 0 plus 0, 0, 0. Right here, I've written it as something in U, something in V, something in W. Or you could write it as, I don't know, 0, 0, 0 plus 0, 0, 0 plus 1, 1, 0. That thing is in W. Right? Or, I mean, there's other ways to write it as a sum of three things. You could take 2, 0, 0 plus 0, 2, 0 minus 1, 1, 0. Right? So there's many ways to write this element as an element of, as a sum of elements, one from U, one from V, one from W. So this sum lacks the uniqueness property. Okay, but you can check, right? So it's not so hard to see that U plus V, this sum of everything in U and everything in V, this is the same thing as U plus V plus W. And here, every element has a unique representation as something in U plus something in V. So this thing you could denote by U plus V with this new symbol. So it is a direct sum. Okay, and actually, it's not just U and V, but it turns out that if you take the direct sum of U and W, the direct sum of V and W, that all three things here are the same subspace, the xy plane, and each of these is a direct sum. Okay, so you should actually check this. So you should actually mess with these vectors and see what happens. Okay, so somehow a direct sum is like a nice way to write a sum of some subspaces. But it seems like the condition for a sum to be a direct sum, in principle, it seems like it involves checking infinitely many things, right? Because the definition is that every vector in the sum can be written in a unique way. Seems like you'd have to check for every single vector, right? But our next theorem will tell us that you don't need to check infinitely many things. Really, you only need to check one thing. Here's the theorem. So again, suppose that U1 through UM are subspaces of V. Then this sum, this subspace, is a direct sum if and only if the only way to write 0 as a sum of elements, one from each of the UIs, is by taking each UI to be the 0 vector. Okay, so what this is saying is that to be a direct sum, you only need to make sure that 0 has a unique representation. Right? Certainly, you can write 0 as 0 plus 0 plus 0 plus 0 plus 0. If it's a direct sum, that better be the only way to do it. And it turns out that that is a necessary and sufficient condition for being a direct sum. Okay, so let me give you the proof. Okay, so let's do this direction. So if this is a direct sum, then by definition, since 0 is in here, there's only one way to write 0 as u1 plus u2 plus um, where each ui is in ui, right? This is just the condition for being a direct sum. Every element has a unique representation like this. And certainly, you can write 0 as 0 plus 0 plus 0. So that means that this must be the only way that you can do it. Right, so that takes care of that direction. What about this direction? I need to show that if 0 has a unique representation as a sum, then actually every element has a unique representation as a sum. Okay, so let's suppose that the unique way to write 0 as a sum is just as a sum of zeros. This is what we're allowed to assume in the converse direction. I need to prove that the sum is a direct sum. I need to prove that every vector can be written in a unique way. Okay, so let's suppose that v is some vector in the sum. Again, I need to show that v has a unique representation as a sum. So let's suppose that I have two different ways to write v. Right, so suppose this, and suppose that v, you can write either as v1 plus v2 up through vm, and as w1 plus w2 up through wm, where each vi and each wi is in ui. Well, what do I need to show? I need to show that these two ways of writing v are actually the same. What am I allowed to assume? I'm allowed to assume that 0 has a unique way of being written as a sum. So what can I do here? Well, the natural thing to do is to subtract these two equations, right? V is both of these things. So subtracting, we have that v is actually v1 minus w1 plus v2 minus w2 plus vm minus wm. Sorry, not v minus v. Right, but v minus v is 0. So what do I have here? Well, since each of the ui's is a subspace, it's closed under subtraction. It's addition and scalar multiplication. So here I've written 0 as a sum of things, one from each of the ui's. And by hypothesis, I assume that there was a unique way to write 0. So this must mean, by our hypothesis, that v minus 1 minus w1 equals 0, v2 minus w2 equals 0, vm minus wm equals 0. Right, which is just the same thing as saying that v1 equals w1, v2 equals w2, vm equals wm. Right? So that means that these two ways that I had to write v, those are actually the same way because each of the vectors in the sum is the same. So this shows that if there's a unique way to write the 0 vector, there's actually a unique way to write every vector in the sum. Okay, so instead of checking infinitely many things, you only need to check one vector. Okay, but in fact, in some ways, an even nicer theorem. But this theorem only applies to if you have a sum of two subspaces. So here's the theorem. If U and W are subspaces of V, then U plus W is a direct sum if and only if U intersect W equals the zero vector. Okay, so in some ways, this is nicer than the previous theorem because the previous theorem involved checking whether zero has a unique representation. But this theorem is sort of easier to understand. It's just what do the subspaces intersect in? But on the other hand, the previous theorem dealt with arbitrary. You can take any number of subspaces and check if it's direct sum. This proposition only handles the case where you're taking the sum of two subspaces. But it's a nice result anyway. So how do we prove it? So let's prove the forward direction first. Let's suppose that U plus W is a direct sum. Okay, I need to show that the intersection between these two subspaces, U and W, is just a zero vector. So let's take a vector V that's in the intersection. Okay, well, V is also in the sum because you can write V as V plus zero. I'm gonna leave some space here. It's in U plus W as well, right? But actually, you can write V not just as V plus zero, but you can also write it as zero plus V, right? Since V is in the intersection, it's in both U and W. So here it's in U and zero's in W. Here zero's in U and V is in W. Okay, so what have I done here? I've written V in two different ways as an element of U plus W. But U plus W is supposed to be a direct sum, which means that there should be only one way to write V, right? So it must mean that actually these two ways must be the same. This way and this way, these must be the same. Since U plus W is direct, it's a direct sum, which means that this V is actually equal to zero. Right, so I've shown that any vector in the intersection must be the zero vector. This means that U and W intersect in just the zero vector. Okay, what about the converse? So conversely, suppose that you have two subspaces that intersect in the zero vector. Okay, I want to show that U plus W is a direct sum. But now I can use the theorem that we just proved. I only need to check if there's only one way to write zero. So by the previous theorem, we just need to check if there's a unique way to write zero as a sum. Right, so suppose that I write zero as a sum where U is in U and W is in W. Well, if U plus W equals zero, this means that U is equal to minus W, right? But now U is in U, but also it's minus W and W is in W, right? This thing is in U, this thing is in W, but W is closed under scalar multiplication, so negative W is in W. So actually the whole thing is in W. So this vector is in both W and U, so it's in the intersection. Okay, but the only thing in the intersection by hypothesis is the zero vector. So this means that U equals W equals zero, which means that the only way to write zero is zero plus zero. is 0 plus 0. But now, by the previous theorem, this means that this sum was actually a direct sum, right? Which proves the proposition. Okay, so I think that's all we'll cover today. What do we learn today? Well, we learned the definition of a subspace. It's just a subset that is itself a vector space. Right? We saw some examples of subspaces, which you should go over. We have this homework exercise that if you take the intersection of any number of subspaces, you again get a subspace. Then we discussed how to combine some subspaces to form a bigger subspace by taking the sum, right? We saw the definition of that, and we proved that that is the smallest subspace which contains each of the individual subspaces. And then we said, okay, well, some of these sums of subspaces have this nice additional property that every vector in them can be written in a unique way as a sum. Those we called direct sums. And we saw one theorem and one proposition which allow you to identify direct sums. One in general, and one sort of easier condition in the case that you took the sum of two subspaces. Okay, so your first homework will cover 1A, 1B, and 1C. It'll be due next Monday. I'll send you an email about that. And then starting next lecture, we'll move on to chapter 2, starting with span and linear independence.